The following question appeared on the 1997 GRE mathematics test. This is a test used to evaluate candidates pursuing a graduate degree in mathematics. The test does not allow the use of a calculator. At how many points in the xy plane do the graphs of y equal x to the 12th and y equal 2 to the x intersect? The answer choices are A, none, B, 1, C, 2, D, 3, and E, 4. Amazingly, only 17% answered correctly. Pause the video and see if you can answer this question correctly and find out if you are smarter than a math major, on this question at least. Although calculators are not allowed on the test, we'll use Desmos for instructional purposes. I have 2 to the x graphed in blue and x to the 12th in red. Most people during the test would have had no trouble making a similar looking sketch, as these are basic exponential and power functions. We can immediately see that one of the intersection points is here and the other one is here. Let's pan up and zoom out to see if there's more. Notice that I've zoomed out to a y value of about 2300, and still there's no intersection points in sight. So we did it. The answer is C, 2, right? Well, let's take a closer look. If we follow Einstein's advice, then we definitely made the problem as simple as possible by sketching the two graphs to find their intersection points, rather than trying to solve them by hand, a task that would be close to impossible, especially without a calculator. But we don't want to make the problem any simpler by ignoring the rest of the graph. From our Desmos sketch, we see that between the two known intersection points, 2 to the x is greater than x to the 12th. We also know that there are no intersection points when x is less than negative 0.947, since 2 to the x is headed to 0 asymptotically, whereas x to the 12th will head to infinity. So we can safely ignore that region. That means we need to investigate what's going on when x is greater than 1.063. The limit of the ratio of our two functions should approach infinity if x to the 12th continues to be larger than 2 to the x for an arbitrarily large x. Because this is a limit involving the indeterminate form of infinity over infinity, we can apply L'Hopital's rule and take the derivative of the numerator and denominator. When we do, we get the following. However, that's still an indeterminate form, so we should keep taking the derivative until the expression is no longer an indeterminate form. Here's the result when we do so. Notice that all the nasty stuff in green is actually just a constant, which we can call k. Now the limit can be written as k over 2 to the x, and this goes to 0, not to infinity. This shows us that 2 to the x must eventually catch up to x to the 12th, and that means that there must be a third intersection point. Intuitively, we might remember from math class that an exponential function will eventually outpace a power function. This leaves us with the question, if b to the x eventually overtakes x to the n, then where does it actually happen for these two functions in our GRE math problem? We could continue to pan and zoom for hours to find it, but let's do a little trick. Let's hide the two functions and graph their difference, which will be shown here in red. That way, the x-intercepts will reveal all x values for which the two functions intersect. And once again, oh no, it looks like only two x-intercepts, here and here. What's going on? Wait. If I zoom out, it looks like we find that third intersection point. And now I'm just going to zoom in, and it looks like it's going to be between 74 and 75. So now we're back to the original graphs, and this time I'm going to set my x-axis from 74 to 75. And then I'm going to set the y-axis from 74 to the 12th to 75 to the 12th. And wow, like magic, it looks like we found that third intersection point, hidden way up in the stratosphere of the y-axis at an astronomically large value of 3 times 10 to the 22nd power. That value, by the way, is just 1 order of magnitude less than the distance in miles from Earth to the edge of the universe. So we now know the intersection points. The first two, which we knew were there all along from just a simple sketch, and the third one, which we know exists thanks to our understanding of exponential and power functions. If you answered D3 to the original question, congratulations, you answered correctly. I hope you enjoyed this video. If you did, please give it a like and consider subscribing. Also, I'd love to get your feedback in the comments. Thanks for watching and see you soon.